Hi, my name is Dennis. Thank you for watching this video. I wanted to make this video quickly on quantum computing because there are people who know me really well know that I have been dabbling with quantum computing and its understanding over the last 2 years. And people have been asking me questions, and I finally decided let me just make a quick video because makes it so much more easier for people to understand the concepts of quantum computing like the way I do. This is my first video, so I am very excited. So thank you for watching this. What am I going to talk about in this video? Let's look at what a regular classical computer is, and what a quantum computer is, and how is it actually different. Let's look at some use cases where quantum computers can actually do a job far better than regular computers. I also want to talk to you a little bit about some of the industry use cases that quantum computers can solve or resolve, either ways, and also about the concepts of quantum superposition and quantum entanglement over here. There are more concepts, but I'd like to, keep this video quick and small and go with that. And more importantly, towards the very end, I've been having people ping me left, right, and center, ask me, hey, where do we invest in? Who are the big players in the quantum space and quantum computing space? And what are my recommendations? So let's get started. So, alrighty. So when you think of a computer, we typically think of a classical computer, right? I mean, either your desktop or your laptop and so on and so forth. So all of these computers typically work on the concept of, bit-based computing, which means that you got these computers have bits which can either turn on or off, one and zero, up or down, however you want to look at it, right? I mean, these are the different states that it can typically take, either one or the other, not all at the same time. Bit-based computers are pretty good when it comes to calculating items in a serial manner. There is the concept of threads and so on and so forth, but typically let's just look at it as a serial computer which can do things really really fast. Now, let's go back a little bit in history. Microprocessors have been around for the last 50 plus years. Intel. I mean, there were companies before Intel, but one of the pioneers in trying to make classical microprocessors built the x86 architecture. I remember using a 386 computer when I was about 10 years old, and then looked at 486s, and then came the Pentium and the Pentium 2, 3, 4, so on and so forth. That's been a journey over there, right? And then over time, people figured out that you could put multiple cores on the same die or the same CPU. And then you had the concept of multi-threading and hyper-threading and so on and so forth. Now, that's all great, uh, but when I talk to you about having a 386 or a 486 or a 58, I mean, a Pentium and so on and so forth, it's like, evolving from having a Corolla to a car to probably a better car and then a BMW. And finally, you got all these, amazing CPUs and GPUs and all of this from NVIDIA. It's like driving a Ferrari or a Lambo or with a Blackwell, it's like getting a Bugatti, right? People who know me know that I love to use cars as an analogy over here. Now, what about quantum computing? Does it mean faster computing? Does it mean, oh, okay, from a Bugatti, now you got like crazier hypercar? No, it's actually not that, right? Quantum computers are different in a manner that, it's not that it allows you to compute faster, it allows you to compute different. How is it? It's like, think about it in this way, right? If you lived on an island and there were other islands around you, um, you could, the faster the car you had, you could actually, traverse around your island really quick. Think of a big island, right? But if you had to get to island number two and three and four and so on and so forth, what you actually need over here is a boat. Even if it is a small little boat or a big ship, you still need a different form of transport. Quantum computing is like having a boat or maybe a submarine, which you can now explore underwater. Does it make it? Is it a faster car? No, it's just different, right? So why is it different? Because quantum computers are built on the concept of quantum physics over here, and when you talk quantum physics, you're now talking about really really small particles, right? Subatomic particles like electrons, protons, neutrons, and so on and so forth. So if I can take a subatomic particle and convert it into a bit, and let's give it a nice fancy name and call it a qubit or a quantum bit. You know, um, I can actually use it for computation, right? So my qubit over here is phenomenal because of the fact that it can compute really fast or compute really different, uh, and in a manner that it can maintain, two of the stages at the same time. So when we talked about a regular computer over here, I talked about a bit either having one or a zero, whereas a qubit can actually be both one and zero at the same time. Uh, to understand that better, let's understand the concept of something called as quantum superposition. Now, let's look at quantum superposition, and let me see if I can explain it in a manner that elementary school kid can understand it, right? So I got a quarter over here, this regular American quarter. You know, we got heads and we got tails, right? What if I were to, excuse me, what if I were to flip this coin really fast? If it were actually turning really quick, if you notice, if I were to stand below the coin and look up, and if I look at the face over here, I would say, hey, you know what? My coin is actually at tails. But at the exact time when I'm looking at it from below the coin, what if you are looking at this on top of the coin and you look at it and what do you see? You say, hey, you know what? The coin is at heads. Are you right? Am I right? Technically we both are, right? It's both heads and tails at the same time, except for the fact that it's all based on how are you observing it. And now what if your coin is flipping at a certain angle, so on and so forth, and every single angle, instead of just you and me, we had like people at 360 degrees around. So all of them could actually say, hey, it's actually tails or actually heads and tails, and every single person around it is actually right, simply because of the fact that this is constantly flipping, and based on how you observe it, it takes a particular state. Now, keeping this concept in your mind, let's go back to a regular bit. A regular bit typically has 0 and 1. So if I have a 1-bit computer, I can represent two values, 0 or 1. A 2-bit computer can actually represent four values because it's 0, 0, 0, 1, 1, 0, and 1, 1, right? So 0 to 3. And 3-bit can actually represent, eight numbers, 0 to 7 technically, right? And 4 bits is 16 and 32 and 64 and so on and so forth. But at any one point of time with a classical computer, all that the computer can understand is just one particular number. It can either be all zeros if it is a 4-bit number, or it could be all ones, which is the number um, uh, you know um, 15 over here, or it could be 0001, which is one, and so on and so forth. It cannot all be the same at the same time, right? Now, if not really if, but a quantum computer is different in a manner that it can understand and look at all possible values at the same time. What it means is a qubit being 0 and 1 shows that the quantum computer can actually see two values at the same time with a single qubit. If I had two qubits, you can see all the four values at the same time. 3 qubits, I can see all the 8 values. So if I were to compute, let me give you another example. Sorry. Let's say we were driving on the interstate over here, right? And while you're driving at 75 miles per hour, and then there are like 40 cars in front of you, scattered around, three or four lanes based on wherever you're driving. And then, about, I don't know, about 3,000 feet away, there is a red car which is driving. And for this example, let's just assume that, what every other car over here is not red. It's either black or blue or gray or whatever else, right? And if I were to ask you, hey, let me just pick me as an example. Hey, Dennis, where is the red car? All I need to do is look at the windshield, look right ahead over there, and say, oh, right over there is a red car. Did I actually need to count, car number one, two, three, four, five, all the way for me to reach the 50th car, which is the red car? No, not really, right? I didn't need to look at the white car and then the gray car and then the black car. I could directly point at a red car simply because I could see all the values in front of me at the exact same time, right? So it's super easy for me to go back and give you a real instantaneous answer saying that the red car is right there and that's where I can spot it. Think of, quantum superposition actually helping quantum computers do this exact same thing, right? I can look at both 0 and 1 at the same time. And the more the number of qubits I have, the quicker I can look at what value I'm trying to look for. And this is what freaked out a lot of people in terms of encryption, right? Hey, uh, uh, can RSA keys be broken real quick and so on and so forth. But let's get to that in a minute. Now, coming back to quantum superposition, the fact that you can look at both the values at the same time helps quantum computers actually analyze large set of data and you know what, give you a near instantaneous answer. And that's what Google's Willow basically did, right? They talked about a regular supercomputer taking, I don't know, a couple of septillion years, and this chip could actually give you an answer in 5 minutes. And the reason being, that it could see all the values and figure out, what value needed to be, picked up over there. So just assume, it's kind of the way how our human brain kind of comprehends data, right? But can we do it linearly much faster than the computer? Not necessarily. Um, what is one of the industry uses of this? Let's say there is data that I am sending, between a NATO country. I'm in the United States, and we were sending data over to, I don't know, let's say Ukraine in this particular case for whatever reason, right? You could have an enemy nation having a sniffer on the network, which could sniff out this data, which is encrypted, and sent across to your fellow country over here, or your allied country. Now, you got to remember, nearly all encryption that you see around you is mathematically secure, right? You take RSA, you take SHA-256, you take any of this. These are all eventually mathematically secure. Well, and the reason classical computers take so long is trying to do a lot of mathematical calculations in a serial manner basically just takes time. That's the reason, classical computers or regular bit-based computers cannot break many of these, encryptions that are 128-bit or 256 bits. When you look at a 256-bit encryption like SHA-256, which Bitcoin is encrypted with, the number of possibilities is as much as, the number of atoms in the known universe. That's hard. That's really hard for you to crack, right? But then you got to understand that, data that these sniffers can typically pick up are pertinent, a couple of years later too. There's a reason why, information is declassified 10, 20 years into the future, right? So if you had these sniffers or enemy sniffers on this network trying to, sniff this, data, and if they had quantum computers that could actually break this encryption, man, you're in a lot of trouble, right? One of the use cases is if you can actually have a wrapper around your regular mathematically encrypted encryption, and have a quantum safe and wrapper around it, makes it a lot more harder for the encryption to be broken. Um, Another example can be, what if I want to look at all possible states of a certain protein synthesis, right? It just makes it so much more easier for a quantum computer to look at, a million trillion different options before you can actually go ahead and say, this is the right one. Let's go ahead and synthesize a drug for this particular treatment. That's something that you can actually do. Now, um, I did talk about superposition. There is another concept that I did want to talk about, and it's called as quantum entanglement. What is quantum entanglement? It's basically where two qubits are, attached to each other. Just think of conjoined twins, except for the fact that they're not conjoined, physically. Irrespective of, whatever state a certain qubit is at, the other, it can automatically define or determine what the entangled qubit is at. Sounds complex, right? I've seen people on the internet talking about it being Einstein's spooky explanation of what quantum physics is, and so on and so forth. The way I look at it is pretty simple, right? If I had a pair of gloves, I have a left-handed glove and a right-handed glove, and they become a pair of gloves. Now, if I took apart and kept two of the gloves aside, to glove number one, put it in a box, and shipped it off to, I don't know, to South Africa. Now, and if I kept the other glove in another box, I bought the one box, gave it to you, asked you to open up the glove, and asked you, hey, look at the glove. And you pick it up and you see that, what, the glove is actually, I don't know, let's say it's a left-handed glove. So my answer to you is, listen, I put the other glove and I shipped it off to South Africa. So what do you think is the other glove? Your immediate answer is going to be, it's a right-handed glove, right? What if I shipped off the box to the moon? What do you think your answer is going to be? Right-handed. What if I shipped it off to Mars? Your answer doesn't change, right? What if I shipped it off to any other part of the universe? Your answer doesn't change. So in a very similar manner, two qubits that are entangled with each other are entangled in a certain manner, which is so easily understandable or calculated in a manner that if a certain qubit is in a certain state, in whatever superposition state it is at, the other qubit is entangled that it's going to be, in an equivalent state. So it makes it so much more easier for you to quickly understand what the second qubit is doing, faster calculations, things like, much more easier for you to, solve certain quantum algorithms. I'll talk a little bit about it too. That's one of the understanding of entanglement over here. So think of it as two clouds. It doesn't matter what it is, and it does actually help. I'm just trying to see if I can pick up more examples over here. But anyways, maybe in quantum cryptography and simulations, it actually really helps. Coming back to what are your quantum safe mechanisms to safeguard yourself and your encryption against quantum attacks. You got NSIT, NISIT, sorry, which creates quantum safe algorithms. The other big corporation that is trying to do a good deal of great, amazing job in quantum encryption is IBM. I believe there are 5 quantum safe encryptions at this point of time. And how does it actually work? It's not typically, this encryption is done using photons. It's not really done using classical bits. I think it's about the scope of this particular discussion. I can make another video trying to explain how light and lasers and photons, technically photons is actually used for quantum encryption. Um, but that's one part of it. There are a lot of other concepts which I believe is about the scope of this particular video. If you want me to talk a little bit more, I can. In future videos, let me know. Uh, Coming back to the last bit of it, there are 2 different algorithms that are typically used to break mathematically secure algorithms or encryption. Shor's and Grover's algorithms. I can again, go back and explain that to you in another video, but at this moment, I know it's a fire hose of information that I've actually given you. Uh, Take it in, soak it in a little bit, ask me questions if you have. I'd be happy to, answer them. The final bit of the video, what are your investment avenues? I am not a financial advisor, so what I'm giving you is not financial advice. Please go ahead and go do your own research. But these are companies that interest me. Uh, Google and Microsoft are 2 big players. They're amazing. But for me, I think the 800-pound gorilla in the room is IBM. They have achieved quantum supremacy. There are Chinese companies that are trying to, build their own quantum computers. I don't know really too much about who and what and how. It's all hidden away in their layers, but I think IBM is the leader. IBM can probably be the next NVIDIA when it comes to quantum computing. But again, hey man, that's what I think. I may be 100% wrong. Who are the smaller players? There are companies like Rigetti. There are companies like IonQ. There are companies like D-Wave. Rigetti is amazing because they are trying to do what Amazon did with the cloud, right? I mean, I don't need to have the whole rack of every single server component in my basement trying to run my company. I can just go to the cloud, get whatever computing that I need, or on demand computing, and be done with it. Rigetti is trying to do something like that. They have the concept of something called as the quantum cloud. I believe it's called as the forest cloud. I don't know if they changed their names, but that's where they are at. I know the stock price went up by 700% over the last 6 months. Anybody who bought in over there, wow, good for you. Well, again, that's not investment advice. So, having said all of this, I hope this gives you a very simplistic, easy way understanding of what quantum computing is. I'd love to make more videos. If you've got more questions, let me know. I specialize in AI and blockchain and in quantum computing. I'm always into next gen, a couple of years behind, what the rest of industry is typically trending towards. If you need help trying to understand quantum computing from a product management perspective, reach out to me. If you need understanding of what blockchain is from a product management perspective, what kind of use cases can you actually go ahead and resolve, let me know. Be happy to help. And of course AI, I don't really need to pitch myself. People who know me know that I am so deep into it. And But there are tons of other experts. So but having said all of this, thank you so much for watching this. Appreciate you taking your time off. Enjoy the rest of your day, and I will talk to you soon. Take care. Bye.